Everybody, my name is J.B. Langston. I'm a senior support engineer at DataStax. I've been at the company about 2.5 years now, and I'm local here in Atlanta. And today I'm going to talk about a subject that's near and dear to my heart, which is troubleshooting Cassandra. So just to get kind of a picture of the room, how many people here are ops people? And how many developers? Okay, Java developers and developers of other languages. Okay, cool. All right, so what I'm gonna do today is first I'm just gonna go over some things to keep in mind while you're troubleshooting. Then I'm gonna briefly touch on some Linux and Java tools that will be useful, and then really the meat of the presentation is going to be a deep dive into nodetool commands and what they show you, as well as things to look for in the system.log. I want to start with just an overview of the troubleshooting process from a support engineer's perspective. First, you need to ask what's changed. Two, you need to determine which nodes have problems, so you know where to look. 3, you need to find and understand the errors that are occurring on the node. 4, examine bottlenecks. 5, determine the root cause. And 6, take corrective action. Now, I'm going to focus today on steps 1 through 4 and the tools that Cassandra gives you to do that. Step 5 and 6 are really kind of the hard part, but that's luckily what DataStax support and a mailing list and Stack Overflow are here to help you do. But I guarantee that if you do the legwork on steps 1 through 4, 5 and 6 will happen a lot quicker. So if we revise that kind of from an end user's perspective, then 5 would be share relevant information, 6 ask for help. So on sharing information, it's definitely better to overshare than undershare. And after doing 1 through 4, you probably have some theories of your own about what's going on, but definitely just keep in mind that you should share all the facts and not just the things that support the theory that you're going with. So what changed? You need to ask yourself first, did it work before? And if it worked before, what did you change? And when I say, what did you change, talking about settings, your application code, has the read and write load on the cluster increased, data volume, the hardware, and networking environment. So aside from did it work before, you can ask yourself, does it work in another environment? And if it works in another environment, compare that environment with this, keeping in mind those points I just brought up. And then finally, have you upgraded? And I don't mean just Cassandra, but also your kernel, your JVM, the drivers, because all of those can interact to create a problem. And lastly, when you're troubleshooting, definitely try to just change one thing at a time, so you isolate your variables and you know what's working and what's not. So next up, I want to talk about some of the processes that Cassandra uses to do its job, and it's good to keep these in mind when we're going through what nodetool and what system.log show you. We're going to touch on the startup process and then the foreground processes, namely coordinating requests and then serving up local reads and local writes from disk. And then there's a bunch of background processes that Cassandra uses. So you've got flushes, compactions, garbage collections, gossip, and hidden handoff, and read repair. And hopefully most of you are familiar with most of those things. Can I see a show of hands? Okay, well, I'm going to explain a lot of stuff as I go along, but I don't have time in my presentation to do like a really in-depth overview, so the audience for this I kind of assumed would have a little experience with Cassandra. See how it goes. The system resources that Cassandra uses are another thing you need to keep in your mind, and these are the same resources that any application uses. You've got CPU, and when we're talking about CPU, you should keep in mind both single and multi-core utilization, because there are certain processes in Cassandra, like compacting on an individual table, for example, that are inherently single-threaded. And so the speed of the single core is still important for those processes. Your memory, and by memory I mean heap space, off heap space, because Cassandra progressively over the years has moved a lot more and more things of the larger data structures off the heap. And so, you know, those don't count against your Java heap space, but they're still included in the resident size of your application. So your application, or your Cassandra process. So if your Cassandra process gets too big, your kernel out memory killer is going to kill it. So keep that in mind. Keep OS page cache in mind, because you know, sometimes I've seen people will have these huge boxes with lots of memory, and they're like, well, if I'm not devoting this memory to Cassandra, I'm not giving into it in heap, then I'm wasting it. But you're not, because the kernel is going to use everything that's left over for page cache, and the page cache is really important for Cassandra to have good performance. Kind of put garbage collection by itself, because although it's driven by memory utilization, it drives CPU utilization, because scanning through all of the heap and trying to determine what's garbage and what's not is a very CPU-intensive process. Disk, both in terms of disk space and I/O bandwidth, your network bandwidth, and then resources, OS resources and limits like file handles, processes, and map memory. Just going to sort of do a quick review of the Linux monitoring commands that I find are the most helpful. Hopefully a lot of you will be familiar with these already. Top for CPU utilization and memory use per process. Top-H, which will give you the CPU utilization per thread. And that's really important with Cassandra, because it's a heavily multi-threaded process, and if you're just looking at the CPU utilization in the overall process, that's pretty opaque. So in order to understand what's really going on with Cassandra, you need to look at it on a thread-by-thread basis. DF for free disk space. IOStat-X to see the I/O bandwidth utilization. Things like how many requests are in the disk queue, how long is the average wait, basically anything about your disk. Free-M to check on how much memory you have free and how much memory is devoted to cache. Netstat-AN so that you can see what connections have been established to what hosts. IFTop is a utility for network bandwidth utilization. And then finally, SAR, which is my favorite really, because it covers most of the above and it gives you history. And having history is really important, because a lot of times you don't know that trouble's coming before it's coming. And so it's really important to be able to go back and correlate a problem that you had, say high latency or any other problem, with the resource utilization on your machine. Also some Java monitoring commands. First, JStack, which gives you status and stack trace of each thread in a Java process. You got jmap-histo, which will give you a histogram of all the objects that you have on your heap. jmap-heap, which will show you the size and usage of each Java heap generation. jstat-gc-cause, I really like this one. It shows you a percentage of, it shows you the percentage of each heap generation, how much is utilized, and it tells you the cause of each garbage collection. And so it's kind of like garbage collection logging, but without having to enable it and restart your process. Next, when you need to bring out the big guns, you've got jmap-dump, which will take a heap dump that you can then load into like Eclipse Memory Analyzer for post-mortem heap dump analysis to see exactly what's consuming your memory. So now, going through that, I kind of getting to the meat of the presentation. And just want to give you a preview of the nodetool commands that I'm going to talk about, which ones I find most useful in my job. Status or ring gives you the overall cluster status. Info will give you status, memory usage, and cache information for a single node. TP stats will give you statistics about each thread pool on a single node. cfstats is going to give you summary statistics for all of the tables on a particular node. cfhistograms will give you more detailed statistics about a particular column family. Proxy histograms is going to give you latency information for requests that a particular node coordinated. So these are, when a client connects to a node, that node becomes the coordinator. It's not necessarily the node that's serving the data off disk. So that's the difference between proxy and cfhistograms. Compaction stats is going to show you the number of pending compactions and the compactions that you have in progress. Netstats is network activity, which includes streams for things like repairs, bootstrap, and so on. Read repairs, and then your in-flight commands that the coordinator has both sent to other nodes and is waiting on a response from. So looking at nodetool status, I'm just going to sort of go through and explain what each of these things are. So first of all, you've got your cluster is divided into data centers. And then in the first column, it tells you whether your node is up or down. And then it tells you the state, which is usually normal. But if the node is either leaving or joining the cluster, or moving its token within the cluster, then that will be indicated there. You got your IP address, and this will normally be your listen address from Cassandra.yaml. But if you specify a broadcast address, that's going to be indicated here, because that's what the nodes tell the other nodes that their IP address is. The load is the amount of data that's stored on a node, and it's normal for the load to vary somewhat from node to node. It doesn't necessarily indicate a problem, but if you have like a huge variance, and I'm talking percentage-wise rather than absolutes, because once you get a lot of data, maybe a gigabyte isn't that much of a terabyte. So, but it can indicate, large discrepancies can indicate some problems like wide rows or partitions, uneven racks, and maybe some compaction issues. Next, you've got the number of tokens on the node. If you're not using vnodes, this is going to be 1. If you're using vnodes, it's usually 256. And then next is the ownership percentage. This is the percentage of the total token ring that this node is responsible for. And I want to bring your attention to the note at the top, which says ownership information does not include topology. What that means is that if you just run nodetool ring or nodetool status without providing a key space, Cassandra doesn't know what replication factor to use. And so it's going to show this information, assuming that you're using a simple strategy and that you have a replication factor of 1. So if you're running this command on a node with multiple data centers, sometimes you need to just take that ownership with a grain of salt unless you've actually provided a key space so that it knows what replication factor you're actually using. Another thing is with vnodes, tokens are randomly distributed to the nodes. And so it's normal with vnodes for there to be maybe 1 or 2 percentage point difference between nodes, but overall they should be roughly the same. Here you've got your host ID, and this is just a unique identifier for the node. It's used with the nodetool remove node command, and also logged for some of the messages in the system.log. And then finally, you've got your rack. And the idea with racks is that you can avoid single points of failure, because typically a physical rack is going to share a power supply, it's going to share a network switch, and so you're ideally wanting to put different replicas of the same data onto a different rack. But I will say, unless you're using vnodes, racks are really more trouble than they're worth because they impose really strict requirements on how you can expand your cluster. And so if you're not using vnodes, I recommend always having all the nodes in the same rack. If you're using vnodes, it becomes much easier, and the only restriction you have to keep in mind is that you need the same number of nodes within each rack to ensure an even data distribution. And then finally, I just want to highlight that line which shows the node that's down in the ring. If you're trying to figure out which system log you need to look at, here's the place that I would start looking. Also, I just want to mention nodetool ring quickly. It's an older way of getting the status, and it shows the same information as nodetool status, except it also shows the token. And when you have vnodes, you're going to have 256 tokens per node, and so each of these lines is going to be duplicated 256 times. It's really hard to read, so that's why I prefer status. Next, nodetool info. This gives you a lot of the same information that nodetool status does, but it's going to give you only for a single node. And so these are the sort of duplicate information. I'm not going to rehash those, but I want to bring your attention to the heap memory and the off-heap memory. So for the heap memory, it's going to show you how much heap is in use and what your maximum heap settings are. And when you look at that, keep in mind that if a garbage collection hasn't run recently, the amount of heap in use may include data that's actually garbage. So if you want to see how much heap, amount of heap that you really are using, you would have to force a garbage collection on the JVM before you look at this number. And in the off-heap memory, that, as I mentioned before, there's a lot of data structures that have been moved off-heap, and that's the total amount of memory that they're consuming. This is a good metric to look at to know if a node's in trouble. It counts the number of exceptions that the node has encountered since it was restarted. Exceptions aren't always synonymous with errors, but they're close enough that this is a really good metric, and if you start to see this number go up, then the node's probably in trouble. You should check it out. Then finally, we've got statistics about the key cache. You've got your size and your capacity. The size is the amount of key cache that's actually being used, and the capacity is the amount that you've specified in your Cassandra diagram. If you see that the size is much smaller than the capacity after your node's been running for a long time serving reads, that's probably an indication that your key cache is too big, so you may want to reduce it. On the other hand, you've got your key cache hits and the number of requests and the hit rate. If your hit rate is low and the size is close to capacity, that may indicate that your key cache is too small. So you may want to incrementally increase that and watch this number until you kind of get to a point of diminishing returns, and that's how you would sort of optimally size your key cache. This is the save period. So periodically, Cassandra will save the contents of the key cache to disk, so that when you restart it, it can reload that from disk, and you're not starting with a completely cold cache. Row cache, you have the same information as you do for key cache, but row cache is really only useful for a really narrow set of use cases, and it's so narrow, in fact, that it's almost not even worth the time to see if row cache is a good idea. So I almost always recommend for this to be turned off, and that's what you see here. Next, we have TP stats, which shows you the statistics for all the different thread pools that Cassandra maintains. And these are the tools that Cassandra uses to do those tasks that I was talking about earlier: serving reads, serving writes, coordinating requests. And I'm going to just go through what the columns mean first, and then I'll talk about some of the more important thread pools. So first, you've got your pool name, which is obviously a description of what the pool does. And then you've got the number of active requests. These are the number of requests that are actively being serviced by a thread. Pending request is the number of requests that are in a queue, waiting for a thread to free up so they can serve them. And the limit for this is typically around 2 billion, but you're going to run out of memory way before you ever hit that limit if you have that many pending requests. A high number of pending requests generally indicates that your node is not keeping up with the demand, and so probably if you see this consistently, it's time to expand your cluster. The number of completed requests is simply how many requests have been completed since the node was last restarted. Blocked is how many requests are currently waiting on I/O. And then all-time blocked is how many requests have been waiting on have ever been blocked for I/O since the node was restarted. And then at the bottom, you'll see a list of message types and the number of times one of those messages has been dropped. Cassandra implements load shedding as a fundamental part of its architecture, so that if a request has been pending longer than the timeout specified in your Cassandra.yaml, those requests will be dropped. And so when you see a bunch of drop requests, again, that's usually an indication that your node is overloaded. Either your disks can't handle it or your CPU can't handle it. But generally, the best approach when you see that start to happen, do some tuning, do some basic investigation to make sure there's nothing obvious going on with your node, but you probably need to expand your cluster at that point. So going through a few of the important thread pools, read stage is the one that handles local reads. So local reads would be actually pulling the data off of disk that a particular replica owns. The number of reads, the number of threads, active threads, is controlled by the concurrent read setting in your Cassandra.yaml. And at the bottom, you'll see we've got the various types of read messages that are handled by the read stage. Next, we got mutation stage. This handles local writes for which this node is a replica. Again, this is local writing to disk, not coordinating requests to other nodes. And again, at the bottom, you have the 3 different types of writes. They're handled by the stage. And then finally, you've got request response stage. And this is the one that actually handles coordination. So your client connects to a node. That node is the coordinator for the duration of your request. And it contacts, based on your consistency level, the number of nodes that you specify, asks for the data, waits for it to come back. So while it's sent out data, it registers a callback with this request response stage. And once the data comes back, the callback is triggered, and that's what this stage handles. At the bottom, you'll also see your request response message. If you see a lot of dropped messages in your request response stage, it generally means that your coordinator is overloaded. And one of the main things that does that is if you're misusing batches. So make sure that you have a valid use case for batches, which the only 2 real use cases for batches is a log batch when you want to guarantee atomicity for a particular set of records. Either they all get inserted or they all fail. And then an unlogged batch is really only useful if you're inserting records with the same partition key. If you're not doing one of those 2 things, then it's better to use your driver's asynchronous query execution and just pipeline requests to round robin around the cluster rather than sending a giant batch to a coordinator that's going to overload it. Flush writer, this one is really important. The number of active threads is governed by the mem-table flush writer setting in your Cassandra.yaml, and then the number of pending tasks is governed by the mem table flush queue size setting in Cassandra.yaml. And the important thing to know about this is that if you run out of available flush riders, that node is going to stop servicing reads until another flush rider becomes available. The flush riders are responsible for writing the mem tables to disk. So a write comes into your node, it goes into the mem table, it goes into the commit log. When the mem table gets full, the flush rider writes it to disk. If it can't write it to disk because all of the flush riders are taken, then it's not safe for the node to accept writes. Your writes are going to back up. You're going to see pending writes come back. And so, if that's the case, that means that your disk is not keeping up with the rate at which you're writing data. So you either need a faster disk. If you're on rotational, you need to switch to SSDs. Adding additional disks to your JBOD configuration or your RAID array can also help. But if that doesn't help or that's not an option, then you need to probably add more nodes. Next, nodetool cfstats is the summary statistics for all of the column families on a particular node. And the thing to keep in mind, all of these numbers apply to that column family only on that node. So if you wanted a cluster-wide aggregation, you would have to run this command on each of the nodes and then add these things up. So the way that this is formatted is you have a key space, and then indented underneath that, you have all the tables in that key space. I'm only showing one here, so it'll fit on the slide. But just realize that there would be a lot of tables normally under a key space. And some of these stats are going to be shown both at the table level and aggregated at the key space level. This is the number of reads that this particular replica has, reads and writes that this particular replica has served from disk. This is the latency for local reads and writes. They're being served from disk. And then this is the number of pending tasks. So the task we just talked about in the TP stats, this is the number of those tasks that are affecting this particular table. Here you have your SS table count, which is the number of individual SS table files that your data is spread across on this node for this particular table. The space used is going to be your the actual amount of space that this table is taking up on disk for this particular node. And again, for the cluster, you have to add up all the nodes to get a total amount for a particular table. And also another thing to keep in mind is because of the way that writes work in Cassandra and that you're never overwriting data in place, this number may be inflated because this might not account for deletes and updates that have occurred since the last compaction took place. Here you have the number of keys that are, it's an estimate of the number of keys that are stored in this table for this particular node. And again, this number might be inflated because the number of keys are counted per SS table. So if you have rows that are spread across multiple SS tables, the number of keys that you have here are going to get counted multiple times. Here you have the amount of memory consumed by off-heap data structures. This is the same number that should be shown in nodetool info. And then at the bottom, you have it broken out by a particular data structure, your bloom filters, your index summary, and your compression metadata. Here you have your stats on the mem table that's currently active for this table. And it's got a cell count, which is the number of columns that are currently stored in the mem table, as well as the number of bytes in the mem table. And then the switch count is how many times that mem table has been flushed to disk for that particular table since the node restarted. And down here you have some statistics about your bloom filters. And briefly, a bloom filter is way for Cassandra to determine whether a particular SS table owns a piece of data, so that it can avoid going and inspecting every table on disk. And so your false positive ratio, the Bloom filters will never return a false negative, but they may return a false positive, in which case the node has to spend extra time checking that file on disk. And so if your false positive ratio is too high, that can affect your read performance. You may want to increase the false positive chance setting, which is a per table setting. Also, the space used at the bottom is sort of the other side of the coin. The higher that you set the false positive chance, the lower you set the false positive chance, the larger the Bloom filter becomes in memory. And so if your Bloom filters are taking up a huge amount of space, then you may have to increase your false positive chance in order to make the Bloom filters fit in memory. And Bloom filters are used on a per row basis, so they grow linearly with the number of rows that you have on a node. At the bottom, we have the number of, we have statistics about the partition sizes. And this is calculated whenever a partition is compacted, so that's why it says compacted partition. But you've got the minimum size, the average size, and the maximum size of the different partitions that have been encountered on your node. And if you have like a huge maximum size that's way bigger than the average, that could indicate that you have a huge partition, which would generally cause problems with data distribution. Your nodes could become uneven, where one node has a lot more data than another. Also, scanning through a huge partition is a good way to generate a lot of garbage that the garbage collector then has to clean up. And so generally you want to avoid really large partitions. And then finally, you have statistics about the average live cells versus tombstones that have been scanned through in the last 5 minutes. And tombstones are the markers for deletes, right? And so when you're doing a query, if you're scanning through a partition and most of the data there is tombstones, you're just generating garbage and you're wasting CPU cycles while the JVM chews through all this deleted data. And so if you see this and the tombstone ratio is very high compared to the live cells, that may indicate that you're doing a lot of deletes and that there's a possible problem with your data model. Next up, we have nodetool CF histograms. This shows you detailed information for a specific table. And you've got the table name and the key space name, then you've got the number of SS tables that each read hit when it was doing queries against this table. And the more SS tables a read has to hit, the slower it's going to be, the more IO it's going to incur. The partition size, again, is going to show you the distribution of data as far as the size of your partitions. And then this is going to show you the number of individual columns that you have in partitions. And the way that you read this is on the left-hand side, each one of these forms a bucket. And so the bucket goes from the previous line, not inclusive, to the current line, inclusive. So at the bottom there, you would have that bucket would contain the number of reads that hit 13 or 14 SS tables. And then on the other side, you have a count. And the thing that's being counted varies by statistic. So you have to look at the column, at the heading, to know what you're counting. So on the first one, you're counting reads. On the other two, you're counting partitions. And then it's also important to pay attention to the units that are used for the buckets. Your buckets are the number of SS tables in the first place, in the first example, bytes in the second, and cells in the third. Here's just an example of how you would read this. This tells you that approximately 14.5 thousand partitions contain between 771 and 920 solved. The CF histograms also shows you the read latency for that table and the write latency. And it's important to note that this latency is reported in terms of microseconds, not milliseconds. So take that into account when you're reading it. And just to give you another example of how you would read this, 1800 writes took between 216 and 258 microseconds. Proxy histograms shows you the same latency statistics, but these are the statistics for the coordinator rather than a local reading for the nodes. And the times shown here are going to include the time that it took for the network traffic to go from the coordinator to the other replicas, and for the number of replicas to apply to meet your consistency level. Next, you got nodetool compaction stats. It shows you the number of pending compactions, and then beneath that, it shows you the progress for the active compactions. And so you've got two types of compactions. You've got normal compactions, which you're combining your SS tables into a larger one, removing any deleted or updated data. And then you've got validation compactions, which really isn't a compaction, but it uses the compaction infrastructure. And the validation compaction is what actually calculates the Merkle trees that are exchanged by a repair in order to determine what data is in sync and what data is out of sync for your nodes. Next, you've got your key space and table name. You've got the bytes completed and the number of total bytes that the compaction is going through, and then you've got a progress indicator in percent. At the bottom, you have the active compaction remaining time. This is just an estimate, and I don't find it typically very useful because it doesn't include the time that the pending tasks are going to take. So as soon as these active tasks finish, you have 7 more waiting. So looking at this number doesn't really tell you a whole lot.
See the same thing in the op center.
Yeah.
With the nets, they just keep coming one after the
Yeah.
other.
So next up, you've got nodetool netstats. This is going to show you primarily your streaming activity, and that's what's highlighted here. And that can be broken down first into the repair session ID, and that's going to be the unique ID of the repair session that these streams are for. Then you've got the IP address of the node that it's exchanging data with. You've got the number of files and the number of bytes total that it's exchanging with that node, and then both sending and receiving. And then you've got the individual files that are being transferred, and below them the percentage complete for that particular file. Then at the bottom, you have some information about read repair, the number of repairs attempted, and the number of actual mismatches that were found. And then here are the coordinator statistics, which will be the number of commands the coordinator sent out and the number of responses received. So that's nodetool, and then the other half of the picture is going to come from the system.log. So system.log is located by default in var log syndrome, and the configuration file is located in etc DSE Cassandra. It's called log4jserver.properties. The important settings in the configuration file are the location, and so it's possible to change where the log is stored, and if you don't find it in the default location, then check your configuration file, find out where it's directed to. Also, this is probably the most important thing that you're going to do. If you normally you'll leave this at info, but if you're trying to diagnose a difficult problem and you don't have enough information, you may temporarily bump this up to debug. And then it's also possible to override the logging on a per class or per package basis. And so if you know you're diagnosing a particular subsystem, Cassandra, you may want to just enable debug logging for that one subsystem, so your logs aren't inundated with debug messages from unrelated things. And then the basic format, we've got the level, which is either going to be info, warning, error, debug. obviously you want to pay special attention to warnings and errors. Then you've got your thread type and ID. This is important when you're correlating messages in a log file because you want to look at what thread logged them. And so, for example, if you got an error from the compaction executor, you may want to look at the previous info message from that thread to see what files it was compacting when the error occurred. Next, you got date and time, which is pretty self-explanatory, but I do want to point out how critical it is to look at the date and time when you're correlating events between multiple nodes. And then next, you have the source file and the line number. Just want to point out that this is in the case of an exception, this would be the source and line number that caught and logged the exception, not necessarily where the exception occurred. And so on that topic, I just kind of want to talk about exceptions for a minute. For the Java developers, this may be a review, but I want to sort of break it down the way a support engineer would look at it. You got your exception at the top, but that's not particularly useful without any context. And so the context is provided by the stack traces. It's a huge wall of text. But the most important thing to understand is at the top, you have the innermost function that was running when the exception occurred. At the bottom, you have the outermost. And so now I'm going to kind of break it down into what the individual components are and what's important to look at. So first, you've got your organization, and this is basically whose fault was the exception. You've got Java, which indicates that it's part of the Java class library. You've got Apache Cassandra, which is the Cassandra open source project. And then you've got com.datastax.bdp, which is the DataStax enterprise product. And in addition to the organization, you'll typically also see a part of the package that concerns the subsystem that was affected by the exception. And so you can look at these and kind of start to get an idea of what was going on. It's got something to do with the cache, for example. You can look at those and start to get a general idea of what those lines were doing. And then you've got your class names. And if the developer did a good job in naming the classes, it should be pretty obvious what that class is for. Even if you've never looked at the code, you should sort of be able to tell maybe what's going on. So, you've got something about key cache serializer, you've got data input string. So if you're getting an EOF exception during an input on the key cache, then you might be thinking, okay, the key cache might be corrupted, maybe I need to delete that file off the disk or something. Just want to point out nested classes are separated by $signs, outermost on the left, innermost on the right. And then finally, you've got your methods, which again, if they're named well, you should sort of be able to tell what's going on. You can see that you're doing a health check at the bottom. You're trying to initialize a column family, which is another name for a table. And then you're deserializing something. And then just to point out, the init in brackets is going to be either a constructor for a class or a static initializer. And then finally, you've got your source file and your line number. The important thing to note is if you're going to go source code diving, is that the line numbers can and often do change between versions. So if you're going to go look at the code, you need to make sure, like if you're on GitHub, that you select the appropriate version from the drop-down before you spend time looking in the code. Another exception that illustrates a few other things, you've got caused by, which indicates a nested exception. And it's common in Java for one piece of code to throw an exception, another piece to catch it, wrap that exception in another exception, and then throw that other exception. So if you're just looking at the outer exception, that may not give you the whole picture. So in the case that you see these caused by, you need to look at both exceptions in order to figure out what's really going on. And the other thing here is the error message, which when you throw an exception, you're given a free-form field in order to provide more details about the error. So this tells us that the type of socket exception that occurred was caused by a connection reset. And then while I've got this up, here are a few more examples of organizations. Org Apache Thrift is a separate Apache project, so if you were going to look at code for Thrift, you would need to look at that project rather than Cassandra. And then again, some of the subsystems, you've got transport, server, Thrift. So if you knew that Thrift was like the old way of interfacing with Cassandra, you can probably guess that this is something to do with the client request. Just want to give a few tips for Googling exceptions, some do's and don'ts. First, you need to use the exception and several of the package plus class plus method names in your search because it's critical to get that context. Use quotation marks around the individual elements so that Google treats them as a whole. This is especially important with an error message which might be broken up into multiple words, and you want that error message to be found verbatim. And then use the cite feature on Google to limit your search to relevant websites. And some of the most useful ones for Cassandra would be the mailing list, the Jira, where bugs are filed, and then Stack Overflow. And for Stack Overflow, you would probably also want to include the keyword Cassandra so that you're only finding things that relate to Cassandra. And then finally, be prepared to narrow or broaden your search as necessary. This is more of an art than a science, and so if you find a ton of results, you may want to add some additional methods and class names to narrow it down. If you don't find any results, experiment with taking some of them out in order to find something. Don't include the source file and the line number because, as I mentioned, the line numbers often change between versions, and if you include the line number, you're often limiting yourself only to an exception that occurred in that particular version. So you might miss troubleshooting information if that also occurred in a different version. And then also don't include specific numbers and strings from the error message. So oftentimes an error message might have like a name of the table or a count of something. And if you include that, obviously, you're not going to hit on anything that is the same class of errors, but has different specifics. So here, just an example of some good search terms on that first exception I showed you. This is probably what I would start with, and then experiment if I didn't find any hits with adding or removing the various methods. And then again, for the other exception, I would include both exceptions, the outer and the nested, and also the error message associated with that exception, and then at least one method name from both exception stack trace. Okay, so just quickly to go through some of the things that Cassandra tells you at startup that can be useful. Logging initialized, that verbatim string is the first thing that ever gets logged when you restart Cassandra. So if you've changed some parameters or something, you may want to exclude anything from the log that was before the final restart because it may no longer be relevant. It'll tell you the version of DSE as well as all the major components, Cassandra, Solar, Spark, what have you. And then it will tell you the configuration file that it's loading the settings from. And this is important because configuration files are pulled out of your class path, and it's possible for a configuration file to accidentally sneak into your class path somewhere other than where you expect it to be. And so I've seen cases where someone was using configuration settings that were totally different from what they thought they were using. So it's always good to check that and make sure your configuration is what you think it is. Data file directories and commit log directories. Again, this just tells you where your files are being stored. It's good to just verify that they are where you think they are. JVM vendor and version. You're going to want to make sure that you're using the Oracle JDK, not Apple JDK, not IBM JDK. because the Oracle JDK is what Cassandra is tested against. Also, make sure that you're using one of the more recent versions of whatever version is appropriate for your version of Cassandra. That's usually going to be Java 1.7 for the current version of Cassandra. And then finally, make sure that you're using a 64-bit JVM. Next, you've got some heap size information, both the overall heap and the size of the individual generations. This is good just to verify your settings, and also if you're looking at the system.log for a node that you don't have direct access to the settings file, then this tells you what those settings were. The class path, if you get some sort of weird error like a class not found exception or a no such method exception, this probably indicates that either you're missing a jar file or you have the wrong version of your jar file. So you want to look at that and make sure that the versions that are listed are the ones that are appropriate for that version of Cassandra. And then finally, JNA and block all successful. You want to look for this verbatim, and if that's not in your system.log, then you don't have JNA installed properly, and that can cause some problems because Cassandra uses that library in order to prevent itself from being swapped out to disk, and for a few other things like taking efficient snapshots. So if that's missing, you need to fix it. And then lastly, you've got started listening for CQL clients and started listening for Thrift clients. This is what tells you that your node is finished starting up and is actually serving requests. So a few other interesting things to look for in your system.log involve the different processes that I talked about. So flushes, first the flush is enqueued, and then it starts writing. When a flush writer becomes available, it starts writing the mem table to disk. And then when it finishes, it logs another message saying that it was completed. And so you're going to correlate the enqueue and the beginning of the write based on the unique identifier of the mem table, which is the part that's highlighted here. And then you're going to correlate the begin and end of the actual flush using the thread name. And then some other information that's useful. This shows you the serialized and live bytes and the number of operations that were in the mem table. Serialized is the size of the mem table when it's written to disk. Live bytes is the number of bytes that it actually consumed in the heap. This is the name of the SS table that the mem table generated when it was flushed, the size of that SS table, and that can actually be smaller than what you saw above because of on-disk compression. And then finally, once a mem table is flushed to disk, that data is safely stored in an SS table, so you no longer need the commit log segment that corresponded to that particular mem table. So this is just the identifier of that segment. And then finally, if you look at the times, you can sort of, by subtracting the second line from, or the first line from the second line, you can see how long that particular flush waited in the queue. By subtracting the second line from the third, you can see how long it took to flush that particular mem table. Compactions. First, you're going to want to look at the name of the compaction thread, which is how you're going to correlate the compactions in the log. And then first, you're going to see that a compaction started. So it's going to say compacting, and then it's going to show you the names of the input SS tables that went into that compaction. When it finishes, it's going to say compacted. It's going to tell you how many source SS tables there were, the output SS table, the number of bytes both going into the compaction and coming out of the compaction, along with a percentage reduction in size. And you're going to have the amount of time the compaction took, as well as the rate of the compaction in megabytes per second. And so Cassandra throttles compactions in order to limit the disk I/O that they generate and allow reads and writes to be served quickly. And so if your compaction took a really long time, you may want to look at whether your disks could actually handle a higher rate of compaction and increase that setting. And then finally, you've got the total number of rows spread across all of the SS tables and how many of those rows were unique. And then you've got the merge counts, which were, this is in the format x:y, where x is the number of SS tables that a particular row was spread across before the compaction, and y is the count of rows that were spread across that particular number of SS tables. I also want to point out, if you see something like this during a compaction, that means you have a wide row that was too large to be compacted in memory. And so if you're trying to figure out what row in your database is a wide row, looking at the system.log and looking for messages like this can tell you which row it is so that you can address it. And it'll show you here the name of the key space and column family and then the partition key for that row. And it'll also show you the size of the row. So you can look at it and see, well, was this row just slightly too large to fit in memory, or is it really, really a huge row that we need to deal with? Garbage collections are the bane of any Java application. Well, there are two types of garbage collections. There are ones that can run concurrently with your application, and there are ones that stop everything while they're running. Stop the world collections means that Cassandra can't serve any reads or writes, it can't gossip with the other nodes. It's basically dead until that compaction completes. The only compactions that Cassandra logs are the stop the world compactions. So you'll see there the type of the compaction, and even though that says concurrent mark sweep, that is actually a stop the world compaction, because what happened was that the concurrent compactor couldn't keep up with the rate at which garbage collection was generated, so the heap filled up. It had to stop the application and compact the heap down before it allowed it to continue. So you see the amount of time here. That was actually 91 seconds that compaction ran for, or not compaction, that garbage collection ran for. And so that is going to wreak havoc on your cluster, right? So that node is, other nodes are going to see that this node is down, they're going to start storing hints for it. Any writes that were in flight to that, reads or writes that were in flight to that node are going to time out. And so it's just a bad deal. On the other hand, this par new compaction, that one's pretty bad. You typically want to avoid compactions that are over like 500 milliseconds, but it's not that bad. But what you also want to look at is the number of compactions that occurred within a particular period of time, because even if the individual, I keep saying compactions, I mean garbage collection, even if the individual collection was fairly short, if you're constantly doing these small collections, your throughput is going to suffer, because the JVM may be spending more time doing these collections than it's actually spending doing useful work. Then finally, if a collection occurs and the heap is still over 75% full after the collection, then you're going to get a warning log that says the heap is a certain percentage full. If that happens, you need to start looking at why your heap is full. You may want to take a heap dump, look at what's filling it up, take corrective action, whether you're going to remove, tweak some settings, move data to a different node, whatever you have to do to get your usage under control. I also just want to point out this message is part of this warning. It says adjust the flush largest min tables at threshold. That's the percentage that warning occurs at, so 75% by default. You don't want to change this setting. You want to address the underlying cause of your usage rather than changing this. And then a subject that's really closely related with garbage collection is called flapping. And you can see here, these nodes are going down, down, up, down, up, down, down. So that's why it's called flapping, is the nodes are constantly going up and down. You can also see it tells you the node that's going down, and it tells you the time that it occurred. And so when you see this in one node's log, you're going to want to look at the log for that other node that's indicated in the error message and see if it's doing garbage collection. See if you can figure out why it's having trouble. If you don't see any garbage collections or any obvious reason that this is happening, then the most likely cause is going to be either network congestion or intermittent connectivity failures. And so you would want to get with your networking team and figure out what's going on there. Hidden handoff, when a node goes up and down, this is part of why flapping is bad. When a node goes down, the coordinator that was going to send data to that replica will store a hint for it. When the node comes back up, the coordinator will send a hint to the node so it doesn't miss the write that it was going to get. And so having hidden handoff occur puts extra load on the coordinator, puts extra load on the node that's going up and down. So this is necessary to help maintain consistency, but it's not something you want to see in your logs. So you'll see here that it started the hidden handoff, it finished the handoff, and you can correlate this again by the thread ID, and then it'll tell you the node that it was sending the hints to and the total number of rows included in the hint. The final thing I wanted to talk about is repairs. So when you run a nodetool repair, looking at the system.log is a good way to gain insight into what's going on with that repair. So when you look at your log, the first thing you want to see is this unique ID for your repair session. That's going to tell you that all of these messages are from the same repair. When you start a repair, you'll see a new session message. Next thing, that message also tells you nodes that it's syncing with, the ranges of tokens that it's syncing, and the key space and column families that it's syncing. Then the first thing that happens when a repair occurs is that it starts requesting Merkle trees from the other replicas for that node. And Merkle trees are the pieces of information, the hash trees that it exchanges in order to see what data is in sync and what data is out of sync with that node. You'll hopefully see, after it's requested a Merkle tree, you'll see that it received the Merkle tree from those nodes. If it didn't receive a Merkle tree from every node that it requested one from, the repair is going to hang at that point. So you need to go look at the other nodes' logs and try to figure out, is the compaction still running? Was there a network error? Why didn't this Merkle tree ever make it back to the node that's requested it? Once it gets the Merkle trees and it does the comparison, it's either going to tell you that the replicas are consistent or that a certain number of ranges are out of sync. If they're out of sync, then it'll start doing a streaming repair, and it'll tell you it's performing streaming repair of this many ranges. And then after that stream completes, you'll see the streaming task succeeded, and so that's your indication that that stream was successful. Finally, once all of the ranges have either been verified to be in sync or the streams have finished, you'll see the message that that particular table is fully synced. And then finally, you should see the message that says that the session completed successfully. If you see a new session message in your logs with a particular session ID and you don't see the corresponding session completed successfully, then that repair didn't finish, and you need to look more closely at the intermediate messages between them in order to figure out why the repair failed or why it's still running. So that's pretty much it. Bringing it full circle, I just wanted to remind you of the steps that I talked about. Next time you're trying to do this, just keep in mind some of the resources that Cassandra gives you to figure these things out, both in the nodetool output and the system.log. And take a look at these things, and it'll help you formulate a much better question if you're asking for help. So that's it. Thanks everybody, and do Q&A now.